All right, team, today we're going to take a look at some graphical interpretation and some ways to organize and display some data. So taking a look at this warm-up question, I just want you to look at it and maybe make some mental observations about what you notice or what you think you're supposed to be getting from this particular graphic. All right, hopefully you had a chance to make some mental notes here. First thing, when I'm looking at this, if this was like, flashed on a new screen really quick, because this is where this graphic was taken, I noticed like my eye is naturally drawn to this highest bar right here. So when we're talking about the Zika virus, it looks like majority of the people are not at all concerned about the Zika virus. So that's kind of like my first impression. However, upon further inspection, if I'm looking at this and I'm actually really looking at the numbers themselves, 13 is the smallest percentage that's being represented, yet it is the tallest bar. So this tells me there's something really, really wrong with this particular graphic. Now look at the largest percentage is actually 34%, yet it's only the second highest bar and is significantly lower than that not at all percentage. And then looking somewhat concerned is 28. That's my next highest amount. That one isn't even represented with a bar. And then not very concerned at 25% is actually more than the 28%. So I can see there's a lot wrong with this particular graphic. You never know the people's intention. Are they trying to was this just an honest mistake where they just put maybe the wrong labels at the bottom, or are they trying to actually mislead you with this particular graphic? So we don't know their intentions, but this is a terrible graphic. And just kind of the idea behind today and our next lesson, our final lesson for this class, is just to get you guys looking at data and thinking about it and just kind of taking it with a grain of salt and just figuring out, okay, is this actually the best representation for the particular data? I will say the only good thing about this particular graphic is the fact that all of the percentages, so if you were to take 34, 28, 25, and 13 and add all of those together, you would end up with 100%, meaning all of the categories, are represented here. So there's not like a missing category that maybe they didn't include in this particular graphic. All right, so for the printout for today, we are going to be looking at this data that's organized here in this table. We'll take a look at a pictograph, and then we will move on to the next section, which is going to talk about frequency distributions and histograms. So we're not going to explicitly talk about bar graphs and line graphs. However, you will see some problems in your homework, and you will have enough information from today just to be able to kind of read the data and answer some relevant questions. So this particular table right here is just looking at some important information regarding particular hurricanes that have hit in the last 30 years or so, 40 years or so. So just kind of take a moment and just kind of go through it, look at the categories, look at some of the numbers, and just, kind of, if you can even, start to formulate some questions that could be asked about this particular set of data. All right, now that you've had a chance to get familiar with this data, let's answer some questions. So these are just some questions that I came up with, and let's see what we can figure out. So for number one, how many hurricanes are being compared? Well, that's where I'm going to go up, and I can just kind of actually count them. So I have 1, 2, 3, 4, 5. So we have 5 different hurricanes that are being compared. And then what is the span of years that are being covered? Well, it looks like the earliest one was 1983, and these do appear to be going in numeric order. In 2005 was our last one. So if we're looking for that span of years, we want to find what's the difference in the years. So the most recent minus the oldest gives us a difference of 22 years. So we're looking at data that's covering 22 years. And then 3, how many categories are there? What are the titles of the categories being compared? Well, there's actually 6 different categories. So we have the hurricane name. So we'll maybe I'll just highlight them up here. So we have the actual name of the hurricane. So there's one category. We have the date in which they fell, the year in which it fell. We have where it hit. We have the maximum sustained winds. We have the number of deaths, and then we have the estimated cost. So those would be the 6 categories that are being compared within this table. Moving on to number 4, how many hurricanes hit Louisiana? This is a tricky one because there's actually 2. So if you notice here, just kind of reading this and getting comfortable, where did it hit landfall for Katrina? It hit in Louisiana and in Mississippi. So that means 2 different states were impacted with that particular hurricane. And if we just kind of keep going down the list, you can see Florida and Louisiana here. So again, 2 different states were impacted when Andrew hit. So how many states hit Louisiana? Or how many hurricanes hit Louisiana? That would be 2. Which hurricane is the most recent? Well, that's going to be Katrina, because 2005 is the most recent one that's being compared here. And then which hurricane was most costly? So that's where I'm going to go down to this estimated cost column. And I'm just going to look down. I have 81.2 billion, 5.8, 35.6, 10.8, and 5.9. So most definitely looks like Katrina was the most expensive hurricane. Number 7, what is the difference in the maximum sustained winds for Andrew and Katrina? So if I find Andrew on here, that's going to be 35.6. Sorry, that's for the winds. So for Andrew, it was 145 and Katrina was 125. So what is that difference? I'm going to take the biggest minus the smallest. And so we have a 20 mile per hour difference. So that means Andrew had a higher wind speed than Katrina did. And then number 8, how many times greater was the cost of Katrina than for Fran? So how many times greater means we're going to find like a multiple. Okay, what is our multiplier to figure out how much more expensive Katrina was than for Fran? So I'm going to go back to the cost column here. And let's find the cost for Katrina. So Katrina was 81.2. And the cost for Fran is 5.8. So here's Katrina, here's Fran. If I actually do that division, I get 14. So that means Katrina was 14 times, had a 14 times greater cost in terms of the damage that was done. And then 9 and 10, this is kind of your opinion here. So which hurricane do you think was the least destructive? So you can kind of decide, what would you look at in terms of making it least destructive? And then number 10, which one was the most destructive? And you can use any of the categories. You can use just one category. You could use all of the categories and really try to compile them. But, just kind of thinking about what would be the least destructive and which one, in your opinion, would be the most destructive. As far as the least destructive one goes, I would probably take a peek at Alicia. This would be my opinion. And Alicia I would say would be the least destructive, because if I go back and I look at some of the data in the table here, let me get this cleaned up. If I'm looking at Alicia, okay, I'm kind of really, the things that I'm looking at are definitely going to be the deaths, because I think that's something that should really be considered, as well as the cost. So Alicia has the fewest deaths. It's not the cheapest. It looks like Fran was just a little bit cheaper, but it wasn't off by a whole lot, but the number of deaths were off by quite a bit. 19 compared to 37 is a pretty big difference. So in my opinion, I would say that Alicia was the least destructive. As far as the most destructive, I would absolutely say Katrina being the most destructive, because that was the most deaths by far, by orders of magnitude. It cost the most, again, by orders of magnitude. Even though it had not the highest maximum sustained windfall, I would still say that one was the most destructive, in my opinion. You can have different opinions here for sure, but this is just kind of my reasoning for the two. All right, next one up, let's take a look at this pictograph. So pictographs are kind of fun. Like, they're just neat looking. Okay, they're visually appealing here. But let's see what we have as far as these questions go. So what is the title of our pictograph? So this is going to be our number of hybrid vehicle sales. What is the value of each of the car icons? So here's my little key off to the side. And I can see that one car is equal to 4,000 vehicles. So every time I see one of those cars, I know I'm going to be working with a total of like 4,000 vehicles. And what's on our horizontal axis here, it looks like the different states that we're looking at. It's not all states, but it's a handful. It's a selection. And what is represented on the vertical axis, this is our number of vehicles. So these are things that I'm always looking at in the beginning just to kind of get myself acquainted with the graph, so that way I kind of have a context of what I'm working with. All right, moving down, number 5, from the graph, estimate the number of hybrid vehicles sold in the state of Washington. So I need to look down here at Washington, and I can see that I have 3 full cars. So I can either do 3 times 4,000 to get 12,000, or I can look over here and say, hey, at my vertical scale right here, here's 12,000, and I'm just kind of looking and see where these two line up. So Washington has, it looks like 12,000 hybrids. For number 6, which state were approximately 10,000 hybrid vehicles sold? So going back to our graphic here, I'm looking for 10,000. Now this one's a little bit tricky because I don't have 10,000 represented on my scale right here. I have 8,000 and then I jump to 12,000. So that means 10,000 has to be right in the middle. So if I'm kind of drawing that line, I can see here that Arizona, since there's only half of a car represented, that must mean that that half a car would represent 2,000 vehicles. So I have 2,000 plus 4,000 plus 4,000 would give me 10,000, or just again looking at the graph and seeing that I have the 10,000 over here and just kind of following along tells me I'm going to have 10,000 vehicles in the state of Arizona. Number 7, how many times more hybrids were sold in Florida than in Oregon? So how many times more, again, means we're looking for a multiplier. And if I am looking at Florida versus Oregon, it looks like Florida is up here at 18,000. And Oregon is here at, it looks like 8,000. So let me go back to the question here. So I'm looking at 18,000 compared to 8,000. So if I go ahead and do that division, so Florida versus Oregon, this gives me about 2.25 times more. Or if you want to think about that in terms of a percentage, this would be like 225% more hybrids were sold in Florida versus Oregon. And then number 8, again, is kind of a personal question here. What would be the pros and cons of a pictograph? So I think a pro is that they're visually appealing. They're kind of cool looking. You know, they're kind of catchy if you're looking at them in an article or something. So I'd say that's a pro. I would say a con, though, is that they are not exact. There was probably not exactly 18,000 hybrids sold in Florida. However, they have to round it to the nearest, like 4,000 mark. So I would say that's definitely a big con, is that they're just not very exact. You don't get the actual numbers here. So just kind of take them with a grain of salt as you're working with them. All right, let's take a look at 9.2. So this is going to be frequency distributions and histograms. So a frequency distribution, I'm just going to go ahead and read this here, is a table displaying the number of values that fall within specific categories. When the categories represent a range of numerical values, we call those categories the class interval. So that's just going to tell us how we're going to split up our data and how we're going to get it organized. So in creating a frequency distribution, there's a few things that we need to keep in mind. Our classes need to be equally spaced, and we look at an example. I'll show you what that means. Just meaning we have the same size category for each. We don't want to have our categories or our classes overlap, meaning if we had some overlapping going on, I wouldn't know where to put a specific data value. So there needs to be a unique category for each kind of set of our data values. And then the third thing, this is just going to be given to us in problems here, but whenever we create a frequency distribution, it's usually kind of good notation just to have between 5 and 15 classes. So a histogram is probably something that you've definitely worked with before. It's a special type of bar graph that illustrates data given in a frequency distribution. The class intervals are given on the horizontal scale, and the height of each bar in the histogram represents the frequency for each class. Furthermore, the bars of the histogram touch with no space between the bars. So let's actually kind of look at organizing some data here. So we have our retirement age in years for 20 college professors. We're going to go ahead and complete this frequency distribution. So don't freak out with the words frequency distribution. All that means is we're just going to organize our data. So right here we have our class interval. So this class interval is going to be the age in years. So when we talked about the classes should be equally spaced, if we look here, we have 3 years that are falling within each class, 56, 57, 58. And then down here, 59, 60, 61. Okay, so I have equally spaced class intervals right here. All of these represent a total of 3 years that would fall into each one of those intervals. The second thing that we talked about was the classes shouldn't overlap. So notice, if I'm working with an age of 59, I know exactly where to put 59. I know 59 would fall into this category right here. Meaning like this category up here wasn't like 56 to 59 and this one was 59 to 61 because then I wouldn't know where to put it. So there's no overlap with the categories. And then we have between 5 and 15 classes. Okay, so we have, looks like 1, 2, 3, 4, 5, 6 classes right here. So we're meeting that requirement as well. So are the class intervals equally spaced? Yes, we have 3 years in each. What is the class interval? Well, it's going to be 3 years. And do the classes overlap? And this would be a no. We have no overlapping. And are there between 5 and 15 classes? We would say yes, we have 6 classes. Okay, so let's actually go ahead and complete this frequency distribution here. So the way I like to do this is just one at a time. If I see 67, let me just kind of clean this up over here. If I see 67, I'm going to find out which interval that falls in, and I'm just going to put a little tally mark right there. So 67 is taken care of. Move on to the next one, 56. So 56 would fall here. 68 would fall here. So I'm going to go ahead and just take a moment and complete this distribution. All right, so I went ahead and I organized all of the data. So I have my tally marks in that middle column, and then the frequency is the number of professors that fall within that category. So the nice thing about doing the tally marks is now I can just go back, and if I have 2 tally marks in this first interval, that means I have 2 professors that fall in that category. So then I would have 1 and 1. This one looks like 7, and then 5, and then 4. So then that's a quick way for me just to sum up how many people fall within each category. So let's look at question E here. Why is there a column for tally marks and another one for the frequency? It just helps us stay organized. The tally marks are what I use when I'm going through and I'm actually trying to organize my data. And then the frequency then lets me sum up my tally marks. And then F, what does a tally of 4 mean in this context? It means that there would be 4 professors who retire between the age of 71 and 73, because that's where my tally mark of 4 was coming from for this particular problem. Moving on, let's look at G. So what age is most likely for retirement based on this data? Well, that's where I want to go and look and see where do I have the highest frequency. So it looks like the 65 to 67 category is the most popular age for retirement based on this data set. What age is the least likely for retirement? Well, those would be my categories that only have 1 person in each. So it looks like 59 all the way up to 64. Since I have 2 categories here that are going to be included. And then I, what is the total number of professors that are sampled? So what you can do is you can actually sum up your frequency here. So take 2 plus 1 plus 1 plus 7 plus 5 plus 4. And we are going to get 20 professors. Okay, other things that you can do, you could count the number of raw data values here. So you could go through and count how many are there. You could also even go back to the original problem, and a lot of times they will tell you, hey, we sampled 20 people, here's the data. And then what percent of professors retire when they are 68 to 70 years old? So 68 to 70 is this category right here. So I have 5. So that would be how many retire out of the total. So 5 divided by 20 is going to give me 0.25. And then I need to convert that to a percentage. So remember, that's when we multiply by 100, and that's moving our decimal point 2 places. So 25% of my professors retire between the age of 68 and 70. And so then for this next question, say if I'm 38 years old and I like to follow data, how many more years of teaching do I have here? Well, I'm 38, and it looks like the most likely retirement age is going to be between 71 and 73 years old. So I've got about 29 years or so more to go. All right. Moving on here, let's look at an actual histogram. So here we have 36 players in the NBA, and we're just looking at the age groups for each of the players. So notice here we have our lovely little histogram. We have the same width for each of our classes. It looks like we have 4 years here. Our bars are touching each other. I have no overlapping categories, and we have between 5 and 15 classes here. So my histogram's looking pretty good just upon initial inspection here. And then let's just answer some questions. So what is our title of our histogram? Well, here's our title. It's going to be the number of players by age group. For N, what does our horizontal axis represent? This would be our age in years. And our vertical axis is going to be the frequency. So all that means is how often does something occur. P, how old is the youngest player? Well, I'm not entirely sure. I know I have this group right here between 20 and 23 years old. So I know it's going to fall somewhere in there between 20 and 23. But I don't know exactly. I don't know what the raw data is going to look like. How old is the oldest player? Well, I know the oldest player is going to be somewhere between 36 and 39 years old. And what age group has the least number of players? Well, looking at my histogram right here, I can read the frequencies. Notice they also are really nice, and they put the frequencies on top of each of the bars to make it really easy to read. So I can either look for the smallest number, or I can look for just that shortest bar. So my shortest bar over here is going to be this older age group. And I would say this is probably what I expect, because professional athletes typically run on the younger age group. And so I would expect fewer NBA players to fall into this older age group category. And then S, how many total players are there? Well, we can go ahead, we can sum all the frequencies. So you can add the 8, 11, 9, 16, and 2, or you can go back up to the original problem. There was 36 total people that were included in this histogram. Now, for this last part right here, I'm actually going to give you the raw data. So this is all the data that was used to compile this histogram. And we can go back now and actually answer questions P and Q. So P was how old is the youngest player? So now I can actually go through and identify what is my smallest data value. It does look like 20 is my smallest. And then for Q, I can go back and look, okay, which one is actually my oldest? And so I'm just kind of scanning this whole thing. I see a 39. So 20 is my youngest and 39 is in fact my oldest, now that I have the raw data to look at. So for T, does the histogram always tell the full story? Not always. Okay, I wasn't sure exactly what these values were because I didn't know what the data points were before. It gives me a really good overall idea, but maybe it doesn't give me all the specifics that I want to see when I'm looking at a data set. All right, so our homework for today will be working in Connect Math on the graph interpretation and the histograms. So I'll be section 9192.